Hi everybody, today let's look at 11.5, Translation, Refractions and Rotations as an Isometry, and 11.6, which is the last subtopic of this chapter, Rotational Symmetry. Okay, let's focus on 11.5 first, Translation, Refractions and Rotations as an Isometry. The name of this chapters is Isometric Transformations. It means that all the transformations that you learned in these chapters, they are an isometry. What is an isometry? If you are given a transformations, after that transformations, every time you draw the image after that particular transformations, the image and the object, they're having the same shape and same size, means that they are congruent. That transformation is an isometry. Translation, refraction, rotations are isometry. So you will notice that every time you draw the image for translations, for diffractions, for rotations, the image and the object will have the same shape and same size. They are congruent. In the futures, you are going to learn another types of transformation, which is enlargement. So here, I show you a little bit about the enlargement so that you know better about what is an enlargement. Enlargement, the image will become bigger or smaller, or sometimes remain unchanged. It depends on the scale factors. So you are going to learn more about this in the future. Okay, now I have an object over here, and this is the center of enlargement, and these are scale factors. I'm going to enlarge this triangle with this at the center, and this is a scale factor that I'm going to use. Even though the name is enlargement, but sometimes it will become smaller. It depends on the scale factors. Okay, let me show you here. Okay, you will see A prime, B prime, C prime. When the scale factor is equal to 1, the image and the object, same size. They have same size, same shape, they are congruent. But when the scale factor change, you see, it sometimes becomes smaller, sometimes become bigger, right? So enlargement is not an isometry. Okay, now let's try some example in this subtopic. In the diagram beside, PQR is the image. This PQR is the image of PST under an isometry. QRS is a straight line. Find the value of X. Okay, the question tells you that PQR is the image of PST under an isometry. We know that the isometry mentioned here is actually a rotation, right? The PT from here rotate to here. The PS from here rotate to here. That's why you notice that there's two same length. And the question doesn't tell you that these two also same length. Actually, PR and PT, they are same length as well. Okay, so now how do we get the angle here? We know that this and this, they are congruent, right? If this is 118, we know here will be 118 as well. 118 as well, right? Okay, so the next thing, the question tells you these two same length. So let me draw for you. So it means that PQS, this is an isosceles triangle. So if this is 51, here must be 51 as well, right? Okay. So the sum of the interior angle for a triangle will be always equal to 180. So if I know this angle, then I can take 180 minus this one, and this one, I will get X. Okay, now I try to figure out this angle first. QPR. The sum of the interior angle of a triangle is equal to 180. That's why I take 180 minus 118 minus 51. Okay, let me press a calculator. 180 minus 118 minus 51. Oh, 118. Let me calculate again. Oh, sorry. 180 minus 118 minus 51 is equal to 11. So this is equal to 11. Okay, now you should be no problem to get the x, right? X plus 11 degree plus this, and this. All these three add up together, you will get 180 degree. So x plus 11 plus 51 plus 51 is equal to 180 degree. So x plus, now press your calculator to get 11 plus 51 plus 51. The value is 113 degree. Okay, so if I ask you to find the x, then you should be no problem. Minus 113, right? 180 minus 113. So this is equal to 7 and 67. X is equal to 67. Okay, let's try one more questions. Triangle ABC. This triangle ABC is the image of triangle PQR under an isometric transformation. Then you know, when you look at the diagram, you know this is a diffraction, right? A diffraction in the line somewhere around here. Okay, so means that this PQR is diffracted in this line, and the image is over here. Okay, so now what's the question asked us to do? Calculate the distance of CR. We want to find the distance from here to here, CR. Given that AP is equal to 20 centimeter. Okay. So here is equal to 20 centimeters. And we know that this part and this part will be the same, right? They're having the same length. This is a diffraction. So if I am able to get the length here, then I will be able to get the length of CR, right? Since that this is a diffraction, if PR is 25, then AC must be 25 as well, correct? Okay, so let me give the length here be y. So now I'm going to find the value of y here. Pythagoras theorem. How to get the y? We take 25 square minus 24 square, and don't forget you have to square root it. Okay, just press the calculator. 25 square minus 24 square. Okay, this is 49. If square root it, you get 7. So now I know here is 7 centimeters. If this is 7 centimeter, we know that here must be 7 centimeter as well. Now we have no problem to get the CR. Okay, so 7 cm plus 20 cm. Oh, let me write again. Plus 7 cm. Then you will get 34 centimeter. Okay, so this is the answer for this question. Okay, let's proceed to the last subtopic, rotational symmetry. So in the before you learn about axis of diffractions, right? Let's say, for example, if you have a shape like this, I just simply draw a shape. Okay, let me draw again. If let's say you have a shape like this, okay, then we have an axial symmetry, right? So okay, axial symmetry is over here, means that when you fold this object along this dotted line, this both sides will map will overlap each other perfectly. So this is for refractional symmetry. So in this chapter, we are going to learn rotational symmetry. When you look at this name, rotational symmetry, you know that it involves rotation, right? Okay. So what is a rotational symmetry? When an object is rotated through one complete turn 360 degrees, if there are at least two positions where the shape look identical, then the object is said to have rotational symmetry. If the object have rotational symmetry, sometimes the question will ask us what is the order. So how to get the orders of rotational symmetry? The orders of rotational symmetry is the number of times a shape look exactly the same as the original shape in one complete turn. Okay, so maybe a little bit confusing, right? These two sentences is okay. Let me show you. So after that, it should be no problem. Now, I have a few shape here. So let's look at these few shape, whether they have rotational symmetry or not. So this is a isosceles triangle. So just now I also draw an isosceles triangle for you, right? So we have an axis of symmetry, but does this have rotational symmetry as well? Let's check. So I'm going to rotate it one complete turn. If you see exactly the same shape as the original shape, then we count as one. All different, right? Only when we go back to the original positions, then they look exactly the same. So in this case, the order of rotational symmetry of this shape is actually 1. If the order is only 1, we say this shape has no rotational symmetry. No rotational symmetry. Okay, we need at least 2, then only the shape is have 2, we need at least the order is 2, then only the object is said to have rotational symmetry. If the order is only 1, we say no rotational symmetry. Okay, let's look at this square. This is a square. Okay, let me turn it. Okay, I need to turn off a full turn. Okay, now you see, look exactly the same, right? Okay, count 1. Again, 2. Again, 3. And when we go back, total we have 4 times. It look identical or exactly the same as the original shape, right? So this shape, this object has rotational symmetry, and the order of the rotational symmetry is equal to 4, because just now we got 4 times, right? So how about this? Okay, let's try. Okay, so I'm going to rotate this object one full turn, 360 degrees. So from here I rotate. Now look different, right? Different. Okay, now exactly the same now. If I move it up, it can actually map overlap each other perfectly. So now calculate 1. Go back. Okay, still different, look different. Okay, another time. When you complete full turn, we have 2 times. Then this object, this shape has rotational symmetry. And the order is order of rotational symmetry is equal to 2. Okay, let's try this one. So this is a regular polygon. This is a regular pentagon. Let's see how many does this have rotational symmetry. If yes, then what's the order? Okay, so now I'm going to turn. That's one full turn. Okay, now look exactly the same, right? 1. Okay, look exactly the same. Okay, okay, so we have one time. Again, 2 times. 3 times. 4 times. And the last, when we go back, 5 times total. So yes, this shape has rotational symmetry, and the orders of rotational symmetry is order of rotational symmetry is equal to 5. Okay, so for a regular polygon, okay, be careful, this is for only regular polygon. The number of axes of symmetry is equal to the number of sides, right? You learned before, I think should be no problem. And today, let's focus on this order of rotational symmetry. The order of rotational symmetry is equal to the number of axes of symmetry. Therefore, we can say that for a regular polygon, remember, only for regular polygon, the order of rotational symmetry is equal to the number of sides. Now we have 5 sides, right? So the order of rotational symmetry is equal to 5. And just now we have a square. Square is a regular polygon as well. 4 sides, the order of rotational symmetry is equal to 4. Okay, so let's try last one. This is a parallelogram. This is not a regular polygon, right? So does this parallelogram have axis of symmetry? No, right? We don't have any axis of symmetry. But how about rotational symmetry? Okay, let's try to rotate it. Oh, I don't have a shape over here. Let me copy first. Okay, so let me rotate it. Now this is original shape, and I'm going to rotate it a full turn, 360 degrees. Okay, now you see it look exactly the same, right? Okay, so remember one time, then go back to the original locations. That total we have 2 times. Then the object has rotational symmetry. The order of rotational symmetry is equal to 2. Okay, so now let's try one more question. Shade 3 more boxes so the figures has rotational symmetry of order 4. So we need to shade 3 more boxes, only 3. And then the final shape will have the order of 4. Okay, so this is the answer. Let me erase first. So how do I get the answer? I can think this way. Since I want to have order of 4, it means that I rotate a 360 degree. I will need to have 4 times look exactly the same. So I take 360 degree divided by 4. I will get 90 degree. So it means that every time I rotate 90 degrees, it will look exactly the same, right? Okay, so how to do that? Okay, so hold on. Okay, let me rotate it. Okay, 1 time, right? Sorry, 1 time. This is 90 degrees, right? When I rotate 90 degrees. Oh, okay, let me try. Okay, hold on, let me change it. Okay, rotate 90 degrees. Okay, so I have to, what should I do? The shaded part become here, so I need to shade this part. Okay, then I rotate some more 90 degrees. The shaded region become this. I need to shade this part as well. Okay, I think better I shade here, huh? So later I can compare. Oh, let me shade again. Okay, let's turn another 90 degrees. Okay, become here. So what should I do? I need to shade this part. Okay. Okay, so when I go back to the original positions, one full turn, the shaded region become here. So already shaded, so do I have to shade? So is this answer correct? We have shaded 3 boxes. So is this shape, the order of rotational symmetry is 4? Okay, let's try. You see, exactly the same, right? 1 time, 2 time, 3 time, and last 4 times. So it means that our answer correct. So this is our final answer for this question. Okay, so for this video, I stop here first. Hope that understand better after watching this video. Thanks for watching and see you next time. Bye bye.